Now let's discuss about the metrics and wave mechanics, or what are the basic difference between this matrix mechanics and wave mechanics. Now the old theory of quantum mechanics basically deals with solving the eigenvalue problem. H psi is equal to E psi, where H is the Hamiltonian of the system, and E is the energy eigenvalue. So this is what we basically do in quantum mechanics. We have to solve this expression. Now this is a general equation and it does not depend on any coordinate system or representation. But to solve it, we need to represent it in a given basis system. Then the complexity associated with solving this eigenvalue equation vary from one basis to another. Suppose you choose a discrete basis to represent this expression, then it yields a matrix eigenvalue problem. So let's consider a discrete basis set phi n, and if you are considering this discrete basis set, then this eigenvalue equation, the same eigenvalue equation will become something like sigma n equal to 1 to n h mn minus E delta mn phi n psi equal to 0. And if you are getting confused how to get this expression, please see the matrix representation of eigenvalue problem that we have discussed earlier in the semester. Then when we have a system of this kind, the system will have a non-zero solution only if this determinant h mn minus E delta mn equal to 0. So this basically gives us an nth order equation in n. When you solve it, you get an nth order equation in the eigenvalue E. So the solution gives the eigenvalue spectrum E1, E2, E3, etc. up to En, and from which we can determine the corresponding eigenvectors phi 1, phi 2, etc. up to phi n. So this we have seen in the matrix representation of eigenvalue problem. So this was the Heisenberg's approach to solve the eigenvalue equation, and it involves only the matrix quantities, and this formulation in quantum mechanics is known as the matrix mechanics. Schrödinger, on the other hand, had an entirely different approach to solve this eigenvalue equation, and he considered the representation in a continuous basis, yielding a differential equation. So the representation of eigenvalue equation, the same eigenvalue equation h psi is equal to E psi in the position space gives, you just need to take the projection onto the position space. So this will give us E into psi, and the Hamiltonian, as you know, it is given by the form of p square by 2m, the momentum operator, plus the potential energy operator, and this in position representation, this Hamiltonian in position representation, you know that p, this momentum operator has some particular form, so this can be written as minus h cross square by 2m del square plus v of r. So this equation can be written as minus h cross square by 2m r del square psi plus we can split that into 2. V of r psi is E r psi, that is minus h cross square by 2m del square psi of r plus V of r into psi of r is equal to E into psi of r, where psi of r is given by the projection of this psi onto this position space. So this is called the psi of r is called the wave function of the system. So what we have in Schrodinger's approach is the wave function of the system, and this differential equation is known as the Schrodinger equation. This differential equation is known as the Schrodinger equation. And the solution of the Schrodinger equation usually yields the energy spectrum of the system as well as its wave function, which we have seen for many examples in the last semester. So this formulation of quantum mechanics in position representation is called the wave mechanics. It's called the wave mechanics. So in wave mechanics, we have a differential equation, and in matrix mechanics, everything that we are dealing is basically matrices.